Hello, in this lecture we'll find out the length of line segment X using two different methods. In the drawing we have a semicircle inside a quarter circle. We know that AO equals to 6 units. Side AC is tangent to the semicircle at this point, and we want to find out the length of side AC that is actually equals to x. So we'll start with the first method. Here actually AO that is equal to 6 units is the radius of the quarter circle, and OB is also the radius of the quarter circle, that is to say, it is also equals to 6 units. But OB is also the diameter of the semicircle. And we know that the diameter of this semicircle equals to 6 units. And the diameter of any circle is twice as large as the radius. So therefore, the radius of this semicircle will be equal to half of the diameter, that is 6 over 2 is 3. So we'll define the center of the semicircle at this point, point P. OP is the radius of the semicircle, and the radius of the semicircle equals to 3 units. It is half of the diameter, that is 6 units. Half of the 6 is 3. Okay, 6 over 2 is 3. So therefore the radius of the semicircle is 3 units. We will define the point of tangency of side AC with this semicircle as point D. We will join actually angle AOB equals to 90 degrees because of the fact that AOB is a quarter circle. So this angle equals to 90 degrees. We will join points P and D together by a straight line. P is the center of the semicircle, and D is a point on the semicircle itself. And this is exactly the definition of a radius. That is to say, PD is the radius of this semicircle that is equal to 3 units. We will join points A and P together by a straight line. Actually, we have a new rule, that is rule number 1. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. I write it down. The lengths of two tangents from a common external point to a circle are equal. I read rule number 1 again. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So actually, if we have this point P, here point P is an external point of this circle because point P is not located inside the circle, nor on the circle, but it is located outside the circle. Therefore, point P is defined as an external point of this circle. So if from point P we draw two tangents to this circle, here the first tangent will be and the point of tangency of the first tangent with this circle is point A. Then we draw the second tangent from point P to this circle. The point of tangency of the second tangent with this circle is B. Then, according to rule number 1, the lengths of two tangents, the length of the first tangent is PA, and the length of the second tangent is PB. And according to rule number 1, the lengths of two tangents from a common external point, that is to say from P to a circle, are equal. 2 points A and B are equal. That is to say, PA is equal to PB according to rule number 1. So whenever you draw two tangents to a circle from a common external point of the circle, then the lengths of those two tangents will be equal to each other. In this case, PA equals to PB. Okay, we can implement rule number 1 in our drawing. We relate to the semicircle from the external point A. The first tangent to this semicircle is AO, and the length of tangent AO is 6 units, and the second tangent from the external point, from the common external point A, is tangent AD. That is to say, according to rule number 1, tangent AO is equal to tangent AD. Why? Because those two tangents exited from the common external point A to this semicircle, and therefore their lengths must be equal to each other according to rule number 1. Okay? It is given us the question that AO equals to 6 units. It is actually the radius of the quarter circle. So from this equation, 6 equals to AO equals to AD, we will derive that AD is also equals to 6 units. Here AD equals to 6 units. You should see that AD is not X, because X is AC. Here AC equals to X, and AD is shorter than AC, okay? Here AD is the second tangent to the semicircle, and it is shorter than tangent AC, that is the tangent of the line segments that we are looking for. Because AC is bigger or larger than tangent AC that is equal to 6 units. Okay, so here actually triangle AOP, this triangle, the right triangle AOP, is congruent to the right triangle APD, according to side rule. Triangle AOP, this triangle is congruent to triangle APD, this triangle, according to side rule. First of all, side AO equals to side AD equals to 6 units. AO equals to AD, and they're both equals to 6 units. We just right now found out that AD equals to 6 units, so AO equals to AD equals to 6 units. AP is the common side that belongs to both triangles, so AP equals to itself. It's a common side, AP equals to AP. It is a common side. And finally, here DP equals to OP equals to 3 units. It is the radius of the semicircle. DP equals to OP equals to 3 units. Okay, so we actually proved that triangle AOP can go into triangle APD according to side rule. Okay, we write it down. Triangle AOP can go into triangle APD according to side rule. And from the fact that those two right triangles can go into each other, we will conclude, hence, we conclude that those two angles are equal to each other. That is to say, angle OAP equals to this angle, that is actually angle PAD, I'll repeat again, angle OAP equals to angle PAD, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the corresponding angles, that is to say those two angles, must be equal to each other. Because they are corresponding angles that are located inside the congruent triangles, therefore they are equal to each other. So if we define angle PAD as theta, then from this equation angle OAP equals to angle PAD equals to theta, we will derive that angle OAP is also equals to theta. Okay, so actually Those two angles, they are both equal to theta. In the next step, we will focus on the right triangle, triangle AOP. On the right triangle, triangle AOP, here tangents theta equals to OP over AO. OP over AO. And repeat again. In the right triangle, triangle AOP, tangents theta equals to OP over AO. OP equals to 3 units, it is the radius of the semicircle. And AO equals to 6 units, it is the radius of the quarter circle. The radius of the quarter circle is twice as large as the radius of the semicircle. So here we found out that tangents theta equals to 3 over 6, that is actually 1 over 2. So in conclusion, tangents theta equals to 1 over 2. Okay, tangents theta equals to 1 over 2. In the next step, we will join points O and C together by a straight line. So what is line segment OC? OC start from the center of the quarter circle. I didn't mention before, but O is the center of the quarter circle. C is a point on the quarter circle itself. And this is exactly the definition of a radius. That is to say, OC is the radius of the quarter circle, that is to say it is equal to 6 units. Okay? In the next step, we will implement the law of cosines in triangle AOC. In the green triangle, triangle AOC. So, I will repeat again on the law of cosines. Actually, I mentioned it in the previous lecture. I will repeat again shortly on the law of cosines. That is true in any triangle. So if we have a triangle ABC, that could be any triangle. This is triangle ABC. We know that side AB of triangle ABC equals to A units in its length. Side AC equals to B units in its length, and side BC equals to C units in its length. And the angle between side AB and side AC is alpha or theta. Then, this is the law of cosines. Then, according to the law of cosines, we get that c squared equals to a squared plus b squared minus 2 times a times b times cosine theta. Okay? So, here we will implement the law of cosines in the green triangle, triangle AOC. So according to the law of cosines, in the green triangle, triangle AOC, maybe I will copy the green triangle, triangle AOC in a new page, and we will implement the law of cosines in triangle AOC. This is triangle AOC. Actually, this is a right angle. So I'll copy it again. Angle. No, it is not right angle. No, it is not a right angle. Angle AOB is a right angle, but angle AOC is not a right angle. So it is okay. So this is triangle AOC. Angle OAC equals to 2 theta. Side AO equals to 6 units. Side AC is the side that we are looking for, and it is equal to x according to what is given us in the question. Side OC is the radius of the quarter circle. That is to say, it is equal to 6 units. So here, according to the law of cosines, we get that OC squared, this will be question number 1, equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta. Okay? And OC equals to 6. Therefore, OC equals to 6. So OC squared is 6 squared, that is 36. And it is equal to AO is 6. AO squared is 6 squared, that is 36. Plus AC squared. AC equals to x, so AC squared is x squared. Minus 2 times AO is 6. So it is minus 2 times 6 times AC is x times cosine 2 theta. So here we have 36 on both sides of equation number 1. So 36 will get cancelled. And we left only with, according to equation number 1, zero equals to x squared minus 2 times 6 is 12. So in conclusion, this expression equals to 12x cosine 2 theta. We will add 12x cosine 2 theta to this equation, and we get that according to equation number 1, x squared equals to 12x cosine 2 theta. We'll divide this equation by x. As you can see here, x is the length of side AC of triangle AOC. Therefore, it can never be equal to 0. That is the reason that we can divide the equation by x, because x can never be equal to 0. Okay? So here we divide this equation number 1 by x, and we get that x equals to 12 times cosine 2 theta. Okay? X equals to 12 times cosine 2 theta. In the next step, we'll focus, actually, I'll present to you trigonometric identity. The trigonometric identity is cosine 2 theta equals to 1 minus tangent squared theta over 1 plus tangent squared theta. Okay? Actually, we have already found out that tangent theta equals to 1 over 2. So we'll substitute tangent theta in this trigonometric identity by 1 over 2, and we'll get that cosine 2 theta equals to 1 minus tangent theta is 1 half. So tangent square theta is 1 half squared, that is 1/4. Over 1 plus tangent square theta. 1 half, tangent theta is 1 half, and tangent square theta is 1 half squared. That is 1/4. 1 minus 1/4 is 3/4, 3 over 4, and 1 plus 1 over 4 is 5 over 4. So here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled. And in conclusion, we found out that cosine theta equals to 3 over 5. Cosine 2 theta equals to 3 over 5. Now we can substitute cosine 2 theta in equation number 1 by 3 over 5. Here we found out that according to equation number 1, x equals to 12 times cosine 2 theta. And we just right now found out that cosine 2 theta equals to 3 over 5. We substitute cosine 2 theta by 3 over 5. Very simple. And we get that x equals to 12 times cosine theta is 3 over 5. 3 over 5. So x equals to 36 over 5. That is actually 7.2 units. Okay? In conclusion, we found out that the length of 9-segment AC, that is actually equals to x, is equal to 7.2 units. Okay? So we finished with the first method. In the next step, I will present to you how to find out the length of side AC that is actually equal to x, according to the second method. In the second method, in the first step we will do the things that we have already done in the first method. Here the point of tendency of tangent AC with this semicircle is point D. The center of the semicircle is point P. PD is the radius of the semicircle that is equal to 3 units. OP equals to 3 units. This is the radius of the semicircle. PB also equals to 3 units. We'll join points A and P together by straight line as we did in the first method. This angle equals to 90 degrees. Actually, in the first method, we proved that the right triangle AOP is congruent to the right triangle APD. I'll write it down. We proved that the right triangle AOP congruent to the right triangle ADP according to side rule, and from that fact we concluded that angle OAP is equal to angle PAD, and we defined one angle as theta, therefore the other angle will be also equal to theta because of the fact that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding angles will be also equal to each other, must be also equal to each other. That is to say, angle OAP must be equal to angle P or PAD. We define one angle as theta, therefore the other angle must be also equal to theta because of the fact that they are equal to each other. Okay, so angle AOP or OAP is equal to angle PAD, and both angles are equal to theta according to our definition. Okay, from here we'll start the second method. Until this point we did the same thing that we have already done in the first method. In the second method we will do another construction that we didn't do in the first method. Here we'll extend line segment AC and line segment OB by a straight line until they intersect with each other. And we'll define the intersection point of the extended line segment AC and the extended line segment OB as E. Okay, actually we created here right triangle AOE. AOE is a right triangle. This is what we did by this construction, we created the right triangle AOE. Here AP is angle bisector. Why? Because it bisects angle OAE into two halves. Each half equals to theta. Therefore, AP is angle bisector of angle OAE. Okay, so in triangle OAE, in the big triangle AOAE, the big right triangle OAE, line segment AP is angle bisector and we actually have the angle bisector theorem. According to the angle bisector theorem, if we have triangle ABC, that could be any triangle. This is triangle ABC. And AD is angle bisector, that is to say, divides angle BAC into two equal parts. This part equals to theta and this part equals to theta. That is to say, AD is defined as angle bisector. Then, according to angle bisector theorem, we will get that AB over AC equals to BD over DC. Okay, I will repeat again. This is actually the angle bisector theorem, that if we have a triangle ABC, that could be any triangle, and AD is the angle bisector, that is to say, divides angle BAC into two halves. One half, the first half is theta, and the second half is also theta. Then, according to angle bisector theorem, the following relationship exists between the parts of this triangle ABC. AB over AC equals to BD over DC. So we can implement the angle bisector theorem in our triangle OAE. Why? Because AP is angle bisector of triangle AOE. It bisects angle OAE into two halves. The first half is theta and the second half is also theta. So according to angle bisector theorem, we will get that here in triangle AOE, in the right triangle AOE, according to the angle bisector theorem, AOE, we will get that here AO over AE, this should be question number 1, AO over AE equals to OP over PE. OP over PE. I repeat again. We implemented the angle bisector theorem in the right triangle AOE. Why? Because AP is angle bisector of angle OAP, OAE. Therefore, according to angle bisector theorem, we will get that AO over AE equals to OP over PE. So here AO equals to 6 units. We substitute AO by 6. AE is AE equals to OP. OP equals to 3 units. It is the radius of the semicircle. It is equal to 3 units over PE. PE is PE. We will leave it as it is. So in conclusion, we found out that according to Engel-Bissector theorem, 6 over AE equals to 3 over PE. We will divide this equation number 1 by 3, and then we will multiply it by AE, and we get that according to equation number 1, 6 over 3 equals to AE over PE. 6 over 3 is 2, so according to equation number 1, we will get that 2 equals to AE over PE. We will multiply equation number 1 by PE, and we will get that according to equation number 1, AE equals to 2 times PE. Okay, AE equals to 2 times PE. That is to say, AE is twice as large as PE. So if we define PE as A, then according to equation number 1, AE will be equal to 2A. Okay? In the next step, we will implement the Pythagoras theorem on the same right triangle, triangle AOE. In the right triangle, triangle AOE, maybe I will copy the right triangle AOE in this new page, and we will implement the Pythagoras theorem on this right triangle, triangle AOE. This is, of course, a right triangle. This angle equals to 90 degrees. OP, here OE equals to 3 plus PE, so you can see from the drawing, side OE equals to 3 plus PE, because OP equals to 3 units plus PE, and PE equals to A, so in conclusion, OE equals to 3 plus A. O equals to 3 plus A. AO is the radius of the quarter circle, that is to say it is equal to 6 units. And we have already found out that AE, according to equation number 1, equals to 2A. Now we will implement the Pythagoras theorem on the right triangle AOE in order to find out the value of A. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, in the right triangle AOE, AO squared this will be equation number 2, AO squared equals to AO squared plus OE squared, of course. The square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say AO squared plus OE squared equals to AE squared. That is the square of the hypotenuse. I repeat again. According to the PT's Pythagoras theorem, a relation for Pythagoras theorem, AO squared plus OE squared equals to AE squared. AO equals to 6 units, therefore AO squared is 6 squared, that is 36, plus OE squared. OE equals to 3 plus A, so OE squared is 3 plus A squared, and it is equal to AE squared. A equals to 2A, therefore A squared is 2A squared. So here, according to question number 2, 36 plus 3 plus A squared equals to 3 squared, that is 9, plus A squared plus 2 times AB, that is actually plus 6A, and it is equal to 2A squared. 2A squared is 4A squared. Here we subtract A squared from this equation, equation number 2. We subtract A squared, and we get, according to equation number 2, 36 plus 9 plus 6A equals to 3A squared. We will divide this equation number 2 by 3, and we will get that over 3 is 12, plus 9 over 3, 9 over 3 is 3, okay, 6 over 3 is 2, and it is equal to A squared. 12 plus 3 is 15, so 15 plus 2A equals to A squared. We subtract 2A and 15 from this equation, equation number 2, and we get that according to equation number 2, A squared minus 2A minus 15 equals to 0. Here the coefficient A equals to 1, the coefficient B equals to minus 2, and the coefficient C equals to minus 15. And the general formula for solving a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times AC over 2a. So here, in our specific quadratic equation, we get that the variable that we are looking for is a, so x equals to a, so a equals to minus b, b equals to 2, so minus b is 2, minus 2 is 2, plus minus square root of b squared. B squared is minus 2 squared, that is 4, minus 4 times 1 is minus 4, times minus 15, over 2a. A is 1, so 2 times 1 is 2. In conclusion, we found out that a equals to 2 plus minus 4 times minus 15 is plus 60, 60 plus 4 is 64. So inside the root we have only 64, that is what is left, over 2. So here we have a equals to 2 plus minus the square root of 64 is 8 over 2. So here we will have two solutions that are possible for a. The first solution is a a1 equals to 2 minus 8 over 2. 2 minus 8 is minus 6. and minus 6 over 2 is minus 3. So A1 equals to minus 3, but because of the fact that A is the length of side PE, and as a length it must be a positive number. A is a length, therefore it must be a positive number. Therefore, it can never be a negative number, so we cancel this solution. A cannot be equal to minus 3, it must be a positive number, and we'll focus on the second solution. The second solution is A2 equals to 2 plus 8 over 2. 2 plus 8 is 10, and 10 over 2 is 5. So we found out that A equals to 5. A equals to 5. So here PE equals to 5 is equal to 5, and PE minus PB equals to EB. Okay, PB, from the drawing it is very easy to see that PE minus PB equals to BE. PE minus PB, PE minus PB equals to BE. That is to say, PE is 5 units, PB is 3 units. So BE equals to 5 minus 3, that is 2 units. BE equals to 2 units. Here BE equals to 2 units. And AE equals to 2A, that is to say AE that is equal to 2A, and A equals to 5, so it is 2 times 5, A equals to 10. And what is the length of CE? A equals to 10 units. And what is the length of CE? Here, CE, for the drawing it is very easy to see that CE equals to AE minus AC. AE minus AC equals to C. Again, AE minus AC equals to CE. So CE equals to AE, that is 10 units, minus AC is the line segment that we are looking for, that is X. Is X. So in conclusion, we found out that C equals to 10 minus X. C equals to 10 minus X. In the next step, we will complete the quarter circle to a circle. So we completed the quarter circle to a circle, and then we will extend line segment PO until it touches the circle, and we will define the touching point of the extended line segment OB in the circle as point M. Point M is the touching point of the extended line segment OB in the circle. What is MO? MO is the radius of the quarter circle. Why? Because line segment MO starts from the center of the circle, that is to say from point O, and ends at point M, that is the point on the circle itself. And this is exactly the definition of a radius. That is to say, OM is the radius of the quarter circle, that is to say, it is equal to 6 units. Very simple. In the next step, I will present to you a new rule. If we draw from an external point of this circle two chords to this circle, we have this point, point P, is an external point of this circle. If from this external point we draw two chords to this circle, this is the first chord, this is the intersection point of the first chord with this circle is defined as point A, and the touching point of the chord with the circle here is point B. In the next step we will draw second chord from point P to this circle. The intersection point of the straight line from point P and the circle will be defined as C, and the touching point of the second chord with this circle will be defined as point D. Then, according to this rule, the following relationship exists between the parts of those two chords of this circle. Here, PA times PB equals to PC times PD. Okay, this is the new rule. And we can implement this new rule in our drawing. I repeat again, if from point P we draw two chords to this circle, the first chord is called AB, the second chord is called CD. Then the following relationship exists between the parts of these two chords. Here PA times PB equals to PC times PD. Again, PA times PB equals to PC times PD. We will implement this new rule in our drawing. According to this new rule in our drawing, we have from the external point E, we have two chords to this circle. The first chord is called EM and the second chord is called EA. So according to the new rule that I presented to you, here we will get that EC times EA equals to EB times EM. I repeat again, EC times EA equals to EB times EM. We have already found out that EC equals to 10 minus x, so we substitute EC by 10 minus x. We have already found out that EA equals to 2A, that is 10 actually, so we substitute EA by 10. And we have already found out that EB equals to 2 units, so we substitute EB by 2. Here EM, what is the length of side EM, of chord EM? Here we have 6 plus 3 plus 3, that is to say 6 plus 6 is 12. 12 plus 2 is 14. So in conclusion, EM equals to 14 units. So we substitute EM by 14. So in conclusion, we found out that 10 minus x times 10 equals to 2 times 14. 2 times 14 is 28, and it is equal to 10 times 10 minus x. Here we divide this equation by 10, and we get that 10 minus x equals to 28 over 10 is 2.8. We will add x to this equation and we will subtract 2.8, and we will get that x equals to 2 minus 2.8. That is 7.2. In conclusion, we found out that x equals to 7.2 units according to the second method. Okay? In the next step, I will summarize the lecture. We'll start with the first method. So I repeat on the question. We have here a semicircle inside the quarter circle. We know that AO equals to 6 units, and we want to find out the length of side AC that is equal to x. Okay, so first of all, we defined the point of tendency of tangent AC with this semicircle as point D. We define the center of the semicircle as point P. Actually, AO is the radius of the quarter circle, and O is the center of the quarter circle, and angle AOB equals to 90 degrees. And OB is also the radius of the quarter circle, because line segment OB starts from the center of the quarter circle and ends at point B, that is the point of the quarter circle itself, and this is exactly the definition of a radius. That is to say, OB equals to 6 units, that is the radius of the quarter circle. But here, OB is the diameter of the semicircle, and diameter of a quarter circle, the diameter of any circle is twice as large as the radius. And we know that the diameter of the quarter circle equals to 6 units. Therefore, the radius will be half of it, that is actually 3 units. So the radius of the quarter circle, the radius of the semicircle equals to 3 units, that is to say OP equals to PB equals to PD equals to 3 units, all those line segments are the radiuses of the semicircle because of the fact that it starts from the center of the semicircle and ends on the semicircle itself. And this is the definition of a radius. Okay, so then I presented to you a new rule that is actually rule number 1. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So we have here point P that is an external point of this circle, and from point P we draw two tangents to this circle. The first tangent is tangent PA, the second tangent is tangent PB, and according to rule number 1, the lengths of those two tangents are equal to each other. That is to say, PA equals to PB. So whenever you draw from a common external point two tangents to a circle, then the lengths of those two tangents will be equal to each other. In this case, PA equals to PB. We can implement rule number 1 in our drawing, because in our drawing we have the external point A. From the external point A, we have two tangents to the semicircle. The first tangent is tangent AO, that is equal to 6 units in its length, and the second tangent is tangent AD. And according to rule number 1, whenever you draw two tangents from a common external point to a circle or to a semicircle, they must be equal in their lengths. In this case, AO equals to AD according to rule number 1. Here AO equals to AD according to rule number 1, but AO equals to 6 units according to what is given as the question, and from this equation 6 equals to AO equals to AD, we derive that AD is also equal to 6 units. Here AD is also equal to 6 units. You should notice that AD is not X, because X equals to AC, and AD is shorter than AC. Okay? So at least we know that the length of X, for sure, it is greater than 6 units, okay? And we join points P and D together by a straight line. PD is the radius of the semicircle. We join points A and P together by a straight line. And here we have those triangle AOP, this triangle, and triangle APD. Those two triangles, those two right triangles, they can go into each other. Why they can go into each other? According to side rule, they can go into each other. Why they can go into each other? First of all, AO equals to AD equals to 6 units. In addition, AP is the common side, it belongs to both triangles, so AP equals to itself, and OP equals to PD equals to 3 units. So all sides of triangle AOP can go into all the sides of triangle APD, therefore those two triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we conclude that angle OAP equals to angle PAD. We conclude that those two angles are equal to each other. According to the rule that corresponding angles that can go into angles are equal to each other. Those two right angles can go into each other. Therefore, those two corresponding angles must be equal to each other. Okay? According to the rule that corresponding angles can go into angles, corresponding angles that can go into angles are equal to each other. So if we define one angle as theta, then the other angle must be also equal to theta. So here, if angle PAD equals to theta, then those two angles are both equal to theta. Then in triangle AOP in this triangle times theta equals to OP over AO in triangle APD in triangle AOP times theta equals to OP over AO. OP equals to 3 units, AO equals to 6 units. That is to say, tangent theta equals to 3 over 6, that is 1/2. So in conclusion, we found out that tangent theta equals to 1/2. Then I presented to you the law of cosines, and we implemented the law of cosines in our drawing. The law of cosines is true in any triangle, so if we have this triangle, triangle ABC, that could be any triangle. We know that side AB equals to A units in its length, side AC equals to B units in its length, side BC equals to C units in its length, and the angle between side AB and side AC is theta. Then according to the law of cosines, C squared equals to A squared plus B squared minus 2 times AB times cosine theta. Okay, you can use this equation, this formula in any triangle, so we'll implement the new of cosines in our triangle. Actually, that is triangle. We'll join points O and C together by a straight line. In this case, we actually created triangle AOC. We'll implement the law of cosines in this green triangle, triangle AOC. I copied the triangle AOC, the green triangle AOC in this page. We know that AO equals to 6 units. AC is the line segment that we are looking for, that is X. And OC is the radius of the quarter circle. Why? Because it starts from the center of the quarter circle and ends at point C, that is the point on the quarter circle itself, and this is exactly the definition of a radius. That is to say, OC equals to 6 units, that is the radius of the quarter circle. And we also know that the angle between side AO and side AC is 2 theta. So we implemented the law of cosines in this triangle, triangle AOC. According to the law of cosines, we will get that OC squared equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta. Okay, OC equals to 6, so OC squared is 6, so this is 36. AO equals also to 6, so AO squared will be also equal to 36. And the AC equals to X, so AC squared is X squared minus 2 times AO, that is 6, times AC, that is X, times cosine 2 theta. So here we have 36 on both sides of equation number 1, so 36 will get cancelled, and we left only with 0, that is equal to X squared minus 2 times 6 is minus 12, so here we have what is left is only minus 12x times cosine 2 theta. So in conclusion, we found out that according to equation number 1, 0 equals to x squared minus 12x times cosine 2 theta. We added 12x cosine 2 theta to this equation, equation number 1, and found out that x squared equals to 12x times cosine 2 theta. We divided equation number 1 by x. It is allowable to divide the equation by x because x is the length of the line segment that we are looking for, and it must be a positive number. It can never be equal to 0, therefore it is allowable to divide by x, equation number 1. We divided equation number 1 by x, and we got the x squared over x is x, 12x over x is 12, so this expression equals to 12 times cosine 2 theta. In conclusion, we found out that according to equation number 1, x equals to 12 times cosine 2 theta. In the next step, we find out the value of cosine 2 theta. Okay? We have trigonometric identity that states that cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. We have already found out that tangent theta equals to 1 over 2, or tangent theta equals to 1 half. So we can substitute tangent theta by 1 half in this trigonometric identity. We did it and we got that cosine 2 theta equals to 1 minus tangent square theta. If tangent theta equals to 1 half, tangent square theta will be equal to 1 half squared, that is 1 over 4. Okay? Over 1 plus tangent square theta, that is actually 1 plus 1 half square. 1 half square is 1 over 4. So in conclusion, we found out that cosine theta equals to 1 minus 1 over 4 over 1 plus 1 over 4. Here 1 minus 1 over 4 is 3 over 4. 1 plus 1 over 4 is 5 over 4. Here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled. And in conclusion, we found out that cosine 2 theta equals to 3 over 5. Now we can substitute cosine theta in equation number 1 by 3 over 5. Okay, here we have, actually we found out that x equals to 12 times cosine 2 theta, and we just right now found out that cosine 2 theta equals to 3 over 5, so we can substitute cosine 2 theta by 3 over 5. We did it and we got that x equals to 12 times cosine 2 theta is 3 over 5. So in conclusion, x equals to 12 times 3 over 5. 12 times 3 is 36, and 36 over 5 is 7.2 units. So in conclusion, we found out that x equals to 7.2 units. Here x, that is actually equals to AC, equals to 7.2 units. We finished with the first method. In the next step, I presented to you how to find out the length of line segment x according to the second method. In the second method, we used the things that we already found out in the first method. Actually, we have already found out that the triangle AOP is congruent to triangle ADP according to side rule. Here, we already found out the triangle AOP equals to triangle AOP is congruent to triangle ADP. Therefore, we can conclude from it that angle OAP equals to angle PAD. And if our angle equals to theta, then the other angle must be also equal to theta. So if those two angles are both equal to theta, according to the rule that corresponding angles in congruent triangles are equal to each other, those two triangles congruent to each other, therefore the two corresponding angles must be also equal to each other. So if one of them equals to theta, then the other one must be also equal to theta. This is exactly what we did in the first method. And then, in the second method, we did another construction. We extended side AD by a straight line, and we extended side OB by a straight line until they intersect with each other at point E. Point E is the intersection point of the extended AD and the extended side line segment OB. Okay, and in this case we created the right triangle AOE. Triangle AOE is a right triangle, and AP is angle bisector of this angle, and OAP bisects it into two halves. Each half is theta, and we have the theorem of the angle bisector. Again, AP is angle bisector of triangle AOAE, the right triangle, and according to the angle bisector theorem, if we have triangle ABC, that could be any triangle. And we know that AD is angle bisector of angle BAC. It divides it to two halves. The first half is theta and the second half is theta. Then, according to angle bisector theorem, the following relationship exists between the sides of the triangle. Here, AB over AC equals to BD over DC. Again, AB over AC equals to BD over DC. We can implement the angle bisector theorem in our drawing because we have side AP that is angle bisector of angle OAP, angle OAE in triangle, the right triangle OAE. Therefore, here, according to the angle bisector theorem, in the right triangle AOE, AP is angle bisector, therefore AO over AE will be equal to OP over PE. In the right triangle AOP, and AP is angle bisector, therefore AO over AE equals to OP over PE. Okay? AO equals to 6 units, AE is AE, OP equals to 3 units, this is the radius of the semicircle, PE is PE. So in conclusion, we found out that according to equation number 1, 6 over AE equals to 3 over PE. We multiplied, we divided equation number 1 by 3 and we multiplied it by AE, and we found out that 6 over 3 equals to AE over PE. 6 over 3 is 2. So in conclusion, we found out that 2, according to equation number 1, 2 equals to AE times PE. We multiplied the equation number 1 by PE, and we got that according to equation number 1, AE equals to 2 times PE. We defined PE as A. Therefore, according to equation number 1, AE will be equal to 2 times PE, that is 2A. So PE equal to A according to our definition, and according to equation number 1, AE must be equal to 2A. So then I drew triangle AOE in this new page. We know that AO equals to 6 units. This is the radius of the quarter circle. This is the right angle. AE is 2A and OE is 3 plus A. Here, OE, this is OP is 3 and PE is A according to our definition. So in conclusion, OE is 3 plus A. OE is 3 plus A. So we implemented the Pythagoras theorem on this right triangle, triangle AOE. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AO square plus OE square equals to AE square, that is the square of the hypotenuse. Here, AE square is the square of the hypotenuse. AO equals to 6, so O square equals to 6 squared, that is 36, plus OE square. OE is 3 plus A, so OE square is 3 plus A squared, and it is equal to AE square. AE is 2A, so AE square is 2A squared. So in conclusion, we found out that 36 plus 3 plus A square equals to 2A squared. So here 36 plus, we open the brackets here, 3 plus A squared equals to 3 squared, that is 9, plus A squared, that is A squared, plus 6A, and it is equal to 2A squared. 2A squared is 4A squared. We subtracted A squared from this equation, equation number 2. We found out that 36 plus 9 plus 6A equals to 3A squared minus A squared is 4A squared minus A squared is 3A squared. So in conclusion, we found out that 36 plus 9 plus 6A equals to 3A squared. We divided equation number 2 by 3, and we got that 36 over 2 is 12, 9 over 3 is 3, and 6A over 3 is 2A, 3A squared over 3 is A squared. So here we have 12 plus 3 plus 2a equals to a squared. 12 plus 3 is 15. So according to equation number 2, we found out that 15 plus 2a equals to a squared. We subtracted 15 and 2a from this equation, equation number 2, and found out that according to equation number 2, a squared minus 2a minus 15 equals to 0. So we have here a quadratic equation. The missing variable here is a. The coefficient a equals to 1, the coefficient b equals to minus 2, and the coefficient c equals to minus 15. And the general formula for solving a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. So the missing variable in our quadratic equation, specific quadratic equation, is a. So x equals to a. So here a will be equal to, according to this formula, minus b. B is minus 2. Minus b is minus 2. Minus 2 is plus 2. Plus minus square root of b squared. B squared is minus 2 squared. Minus 2 squared is 4. Minus 4 times a is 1. And c is minus 15. So this expression equals in conclusion to minus 4 times minus 15 over 2a. A is 1, so 2 times 1 is 2. So inside the root we have minus 4 times minus 15 is plus 16, plus 60, plus 60, and 60 plus 4 is 64. So inside the root we have left only 64. So in conclusion, found out that a equals to 2 plus minus square root of 64 over 2. The square root of 64 is 8. So here we will have two solutions that are possible for a. A equals to 2 plus minus 8 over 2. The first solution for a is that a equals to, a1 equals to 2 minus 8 over 2. 2 minus 8 is minus 6, and minus 6 over 2 is minus 3. But because of the fact that a is the length of side PE, it must be a positive number. It can never be a negative number. So we cancel this solution, and we left only with the second solution, that a2 equals to 2 plus 8 over 2. 2 plus 8 is 10, and 10 over 2 is 5. So in conclusion, found out that a equals to 5 units. Here a equals to 5 units. And we know that a equals to 2a. So 2a is 2 times 5, that is 10. So a equals to 10 units. And what is the length of BE? BE equals to PE, that is a, minus PB, that is 3. Again, PE minus PB equals to BE, PE equals to 8, that is 5, PB equals to 3, that is the radius of the semicircle. So in conclusion, found out that BE equals to 2 units. Here, BE equals to 2 units. And CE, what is the length of CE? We know that AE equals to 10 units. AC equals to X. And CE equals to AE minus AC. AE is 10 units. AC is X. So in conclusion, found out that CE equals to 10 minus X. So C equals to 10 minus X, and B equals to 2 units. Okay. Then I presented to you a new rule. Here we have the example point P. Here from point P we draw two chords to this circle. The first chord is called AB, the second chord is called CD. Then the following relationship exists between the parts of those two chords. According to this rule, we get that PA times PB equals to PC times PD. Again, PA times PB equals to PC times PD. So we can implement this new rule in our drawing. Why? Because here we have the external point A. Actually, before that, we made the construction, we completed the quarter circle to a circle, and in this way we created here, we have the external point E. From the external point E, we have the first chord that is called CA, and here we actually extended the line segment EO by a straight line until it touches the circle at point M, and OM is the radius of the quarter circle because it starts from the center of the quarter circle and ends at point M, that is the point of the circle itself. Therefore, OM is the radius of the quarter circle and also the radius of the circle, that is to say it is equal to 6. So here we have the second chord. From point E, we have the second chord of this circle that is actually called BM. And according to the rule that I mentioned, here EC times EA must be equal to EB times EM. Okay? EC times EA must be equal to EB times EM. EC equals to 10 minus X, EA equals to 10, EB equals to 2, and EM equals to, what is the length of EM? EM equals to 6 plus 3 plus 3, this is 12, 12 plus 2 is 14, so EM equals to 14. Okay, EM equals to 14, so we conclude found out that 10 minus X times 10 equals to 2 times 14. 2 times 14 is 28, so 10 times 10 minus X equals to 28. We divided this equation by 10, and we got that 10 minus X equals to 2.8. We added X to this equation and we subtracted 2.8, and we found out that X equals to 8 minus 2.8, that is actually 7.2. So in conclusion, we found out that X equals to 7.2 according to the second method also. Okay, so in both methods, we found out that the value of line segment X, that is actually AC, it is equal to 7.2 units. Okay, thank you very much.